In this lecture, we will have a first look at a very important type of functions, obviously exponential functions. These are very important functions for at least two reasons that I care to mention now. The first one is that they are important mathematically. They are the basis for a lot of additional functions which come into the study of mathematics later on, and they're important on their own because of some special properties that they have. But not only from the mathematical point of view, they're also important from the applied point of view, as these three pictures try to suggest. In fact, you may probably already have heard the fact that when you're studying population growth, as represented by the picture on the left, or radioactive decay, represented by the picture in the middle, or even growth of money, as represented by the picture on the right, and here of course I'm not talking about growing money on a tree, but growing through investments, then these three kinds of processes are three of the processes that can be nicely described through exponential functions. At the end of this class, I will show you how these phenomena are actually related to exponential functions. Unfortunately, I will not be able to explain to you why. You will have to wait for that until we have developed quite a few more tools in the calculus arsenal, and be able to understand more about derivatives and integrals and differential equations and so on, in order to see why this is true. However, for now I just ask you to trust me, to believe me, and if you don't, just go and look it up. But it is true. Under certain conditions, all three of these processes and more processes as well can be described through exponential functions. So again, important functions from the mathematical point of view, important functions from the applications point of view, and therefore they're worth studying and understanding well. Well, what does an exponential function look like? Well, here it is. How do we recognize an exponential function? Well, just through the way it looks like in the formula. An exponential function looks like this. Nothing very exciting, is it? But in fact, it's a simple building block, as I said earlier, and it can be used then to construct much bigger buildings. I assume that you're familiar with the notation for functions, so you understand what this formula means, but just as a way of a quick review, remember that in this formula, y represents the output or the dependent variable, x represents the input or the independent variable, and the one important thing to notice about exponential functions is that in these functions, this independent variable, the x that we're familiar with, is actually sitting in the exponent of a power. And then of course the third item in this formula is a. A will represent a fixed positive constant. Why do we want it constant? Well, because remember, this a is going to be in the base. It's the base of a power. Well, if we take a negative number as the base of a power, we're going to run into all kinds of problems. Like for instance, if we take a negative power and raise it to an even number, then we end up with a positive number. But if we raise it to an odd power, we end up still with a negative number. Well, what happens with fractions? Well, we can take the square root, or can we take the square root of a negative number? No, we can't, but we can take the cube root. We can take the fifth root, but not the sixth root, and so on. And so you can see that we end up with all kinds of complications if we allow for negative bases. So we're going to assume that this number a in the base is going to be positive and stay away from the complications. This does not detract anything at all from the usefulness and the importance of these functions. Now, you may notice that the formula for an exponential function looks very similar to that of a power function. So we better understand very clearly where is the difference, because it's an important difference. Power functions and exponential functions are very different, have very different properties, and so we need to distinguish them clearly. So we've already seen that an exponential function looks like y equals a to the x. Well, what does a power function look like? Just a little bit of a refresher. A power function looks, well, almost the same. But you can see the difference quite clearly. In an exponential function, the independent variable is in the exponent. That's why we call them exponential functions, because the variable is in the exponent. On the other hand, in a power function, the independent variable is in the base. It's a power function because the independent variable is being raised to a power. There is another difference, of course, a little bit more technical, but also worth remembering. In a power function, the constant a can be any number. We can raise x to any number. On the other hand, for exponential function, as we've just seen, we require the base to be a positive number. What do these exponential functions look like? Well, you may want to arm yourself with a graphing calculator and follow with me and then see if you get the same results, and then perhaps after you're done watching what I'm doing, maybe continue the exploration in a similar vein. We're going to start by assuming that the base is not only positive but actually bigger than 1, and we're going to see in a minute why that is so. So once again, follow me with your graphing calculator and try to graph the function y equals 2 to the power x. And if everything goes right, you should get a graph that looks like this. Well, it's a fairly simple function. It goes up, and yeah, we're going to see a few more features in a minute, but for now that will suffice. But remember, a is good, can be any number greater than 1. Okay, so let's change that and use 3 to the power x. Well, what we get is a shape which is very similar. The only thing that changes is the steepness of the curve. You will notice that this new exponential function with a bigger base will actually have a steeper slope, a steeper appearance. Well, let's see if that remains if we use even bigger numbers. If we use 4 to the power x, this is what we get. Yes, even steeper. Well, what happens if we take smaller bases, still bigger than 1, like for instance 1.5? Well, as expected, this is going to be a less steep curve, but still same shape. And of course, the same thing if we get something even with the smaller bases. Now, a little question for you to think about. What happens if I'm actually going to use a equal 1? I'm going to leave that to you because it's extremely simple, so I'm sure you can handle it on your own. Now, if you look at all these functions and if you play with some more exponential functions with a base greater than 1, you're going to notice that there are some commonalities among all of them. So for instance, you'll notice that the graph is always positive. A to the x is always greater than 0. Well, that makes sense because of course if you take a positive number and you raise it to any power, then you're still going to end up with a positive number. So the graph of these functions are always going to be above the x-axis. Now also we notice that they all have one point in common, namely the point 0, 1, the point that you see in blue there. That's also not surprising because if you take any positive number and you raise it to the power 0, what do you get? Well, any number, positive or negative actually, to the power 0 is equal to 1. And so we're going to end up with the point 0, 1. Now, I said any number, positive or negative, but remember, we're dealing with exponential functions. It's only positive bases that we're using. The next thing is that these are all increasing. Now, I cannot prove that without using derivatives, but you can notice that just by looking at the graphs. And the other thing you can look at is the fact that they're all concave up. Again, I cannot prove it right now, but once we go through derivatives, we can figure it out. And also, all of these graphs have the x-axis as a left horizontal asymptote. These graphs, they all get closer and closer and closer to the x-axis as the graph goes to the left, but they never touch it. However, again, the never touch it part is something we're going to revisit once we study asymptotes. And at that point, I'm also going to show you why, in fact, x-axis for these functions is a left horizontal asymptote. Let's have a look now at what happens for exponential functions where the base is actually less than 1. Still positive, but less than 1. Well, let's play with it. If I use 0.8 to the power x, this is what I get. Same or similar shape. The big difference, of course, is that now the pattern seems to be reversed. You can see that this graph now goes down instead of going up. The function is decreasing instead of being increasing. What about a smaller number, 0.5? Yeah, same pattern, but now steeper. Now notice that the smaller the base is becoming, the steeper, in fact, the curve becomes. And we can see again the same thing with 0.3 to the power x and even more with 0.1 to the power x. Okay. So what do we notice in common about all these graphs? Again, they're all above the x-axis. This is something that we have seen before, and there's no reason why it should change now. 0, 1 is still the point in common. Okay, and functions, however, now are decreasing. Once again, we have to wait for derivatives to check that point. And it's still concave up. The concavity is not going to change. Okay, we're going to see again later on why that is so. And this time the x-axis is a right horizontal asymptote. So it is still an asymptote, and again in high school probably you have already seen this idea of asymptote. We're going to see in more details later, but you'll notice that all of these functions have the x-axis as a horizontal asymptote on the right hand side. Now, there may be some other things which are in common, and I'm going to encourage you to look for them. So play with these graphs, use different numbers, and see if you can find something else that is in common, or maybe something which is different. Now, like in anything else, as they say, the devil is in the details, and so sometimes you have to be very, very careful with the details of these functions. So I'm going to show you a few initial details that are important. We're going to see some later on. First of all, I'm going to show you a couple of functions that may not look like exponential functions to begin with, but that actually are exponential functions if we write them in the proper way. What am I talking about? Let's look at this function, y equals 3 to the negative x. Now, at first sight, and given the definition I gave you earlier, this does not look like an exponential function because the exponent is not just x, it's negative x. And remember, an exponential function has to be of the form a to the power x. But what I can do is I can use properties of exponents to rewrite that function as 1/3 to the power x. So in other words, I'm applying the negative in the exponent to 3 to make it into a 1/3. And by the way, if you're a little bit rusty on how to handle exponents and what they mean and how to play with them, you may want to refresh your memory on that. But if I do that, that becomes 1/3 to the power x, which is definitely an exponential function. Similar thing if I apply this to the square root of 3 to the power x, because I can write that as root 3 all to the power x. Root 3 is a positive number, and therefore I can do that, and this is again an exponential function. However, there are some functions that may look exponential, but they're not. Well, I'm going to still insist and recommend that at this point, the functions I'm going to show you, you do not consider them as exponential. Why? As I said, details, very small details, but details that may be important in what we're doing later. So for instance, if I look at y equals x to the x, well, this is the most blatantly non-exponential function. Why not? Well, remember, how is the base supposed to be in an exponential function? It's supposed to be constant, right? But the base here is x, and that is not constant. So in this case, we don't have an exponential function because of that problem. Or let's look at this. This looks almost okay, but again, the exponent has a +2 in there. Can we get out of this situation just like we did with the 3 to the minus x? Well, not quite. If I use laws of exponents, I can write this as 3 to the x times 3 squared. Well, it's the same thing as 9 times 3 to the x. Well, it's that 9 that creates the problem. This is almost an exponential function. In fact, many people would say this is an exponential function, but technically it is not really. It's a multiple of an exponential function. And as we're going to see later, this is going to create a little tiny detail, not a big one, not one that creates a lot of problems, but a little tiny issue when it comes to computing derivatives and integrals later on. How about something like this? Well, obviously this is not an exponential. It does have an exponential term, but that term of course is added to a 1 and it's in the denominator and so on and so on. So this is a function which will inherit some properties of exponential functions, but it's not an exponential function itself, and we should not treat it as such. So you may want to explore a little bit what the properties of this function would be. And finally, something like this. This is a bit tricky, okay? What does negative 3 to the power x mean? Well, without brackets, we have to follow the law of priority of operations. And those tell us that, in fact, the operation of power comes before the operation of multiplication. That means that this really should be interpreted as minus bracket 3 to the power x. If we're considering minus 3 to the power x, well, first of all, that's not a proper thing to do because remember, for exponential functions, we want the base to be positive, but also we're violating the rules for priority of operations. So in this case, once again, we have a coefficient of -1, which makes this function, properly speaking, not an exponential. Again, not a big detail, but one that you may want to consider carefully in what comes later. there is a very important number that is related to exponential functions, and probably you have heard about this number before. Now, I'm going to introduce it to you and give you a definition that is going to be very useful later, and we're going to use it all the time when it comes to this special number. But the idea is the following. Remember that we noticed that all exponential functions go through this common point 0, 1, the blue point that you see on the graph. But they all go through that point with a different slope. For instance, the function 2d dx goes with this slope, and because the base is a reasonably small number too, then this slope is also fairly small. If we look at the function y equals 4 to the power x, then the tangent line and therefore the slope is going to be steeper, it's going to be bigger. Okay? So now, for a number of reasons which will become more apparent later, it may be nice to have an exponential function whose slope at this common point is exactly 1. So in other words, a function, an exponential function, whose tangent line will have equation y equals x plus 1. X because the slope would be 1, and plus 1 because it goes to the point 0, 1. And so the question is, does it happen? Is there an exponential function that does have that slope? Well, if you look back at this graph, you'll notice that the slope for 2 to the power x is actually less than 1. The slope for 4 to the power x is actually bigger than 1. So, well, it stands to reason that there should be a number that does that. And in fact, the answer is yes, there is. It in fact happens for the function that we call e to the power x. So this magic number is a number, a very special number that in mathematics is denoted with the letter e. In fact, it's one of only 2 real numbers that have their own letter, the other one of course being pi. All right, so this is what we call the natural exponential function, y equals e to the x, where the base is this special number e. So once again, remember e, this number e is defined by the property that the exponential function y equals e to the x has a slope of 1 at the common point 0, 1. Keep that in mind. So why is it called natural? Well, because once we deal with this particular function, all kinds of computations and operations and so on end up being done in a very natural and easy way. So what kind of number is it? Well, it's going to be between 2 and 4, as we have seen. It's an irrational number, unfortunately, just like pi, and that's why we cannot write it down as a fraction. It has a non-repeating infinite expansion in its digital form, and approximately, if we look at the first few digits, it's going to look like 2.7182818, and know that 8 is not going to repeat much more after that. It's enough if you remember 2.7 or 2.71 or 2.72, which is actually the proper rounding value of this number. Again, it's an important value, it's an important number, one that will come up again over and over again, and it has lots and lots of uses because of this property. Again, remember this, the basic, most important defining quality of this number is that the exponential function e to the x has a slope of 1 at the common point. So I mentioned at the beginning that there are some applications of these exponential functions, so I'm going to give you just a general idea of what these applications are. The first one is the following. If you have a quantity, a positive quantity, actually we're going to consider only something real, so positive, that increases at a rate that is proportional to its size. So the bigger it is, the faster it increases. Then it makes sense to describe this function. It's proper, it's a good description of this function to say that it follows this form. The quantity p is going to be equal to some constant c times an exponential function, e to the k, which is itself a number, to the power of t, where t of course is the input in this situation. By using properties of exponents, we can simplify this expression to simply c times e to the kt, and that's the form that we'll be using from now on. In this formula, c is some positive quantity, which represents the initial amount of this quantity, whatever it is that we're looking at. T is the time since the start of the observation. And k, which is a positive number also, is going to be the proportional rate of growth. So it tells it's a number that tells us what proportion of the initial amount gets added every unit of time. So when we have a situation like this, we'll talk about an exponential growth process, and this is where population size comes in as well as invested capital. Both of these quantities grow according to this exponential growth model. We can do the same kind of game by looking at quantities which actually decrease at a rate which is proportional to its size. So the bigger it is, the faster it decreases. Okay? So in this situation, then this quantity can be also properly described by a function of this form, c times e to the minus k, and where again that's going to be a number to the power t. And here, just like before, we can simplify the expression to c e to the minus kt, where just like before, c is the initial amount, t is the time since start, and k is the proportional rate of decay. This time, the quantity, whatever it is that we're looking at, is getting smaller. So in this situation, we're going to talk about an exponential decay. And typical examples of this would be radioactive decay, as I mentioned earlier, and also drug absorption, which is something which is used in medicine, pharmacokinetics, and things like this. So these are the very generic. I'm not giving you any specific example. We're going to see some of those in class, but these are just some generic ideas for how these exponential functions are used. Notice once again that what we're dealing with here is truly not an exponential function because there is that coefficient c in front, but this is one of those situations where that coefficient is not really going to change any of the properties of the functions in these particular applications. However, keep in mind it's a little bit of a detail that you definitely need to watch for when it actually is important.